Record. Okay, so last time we did the limiting reactant problems in chemistry units. So the chemistry happens atom to atom, which a certain number of atoms is a mole. So we also can say that chemistry happens mole to mole, like a mole of oxygen reacts with 2 moles of hydrogen to make 2 moles of water. Okay, you could also say that same with atoms and molecules. But then in the lab, we don't measure moles, we measure mass, and then we use molar mass to convert. So now in these problems with Alex, they turn up the heat a little bit and they start giving us masses of everything. So this is giving us 14 grams of methane and 89.4 grams of oxygen. In the future, they'll add one more layer of complication in that we don't, how are you going to weigh out methane? It's a gas. So we would measure a volume of gas or a pressure of gas and use the ideal gas law to get to moles, okay? But at this point, that's adding too much complication, so we're just going to stick with masses of methane, masses of oxygen, and so on. So what's the maximum mass of water that could be produced by the chemical? So step 1, write the balanced chemical equation. So we've got that. We had to balance it with the waters to get the oxygens. And so then step 2, we see this problem and an alarm bell should go off, little red lights in your head. When you're reading a problem, you see you've got the reactants in orange, I've put the products in blue, and then I see grams of methane, which is a reactant, and grams of oxygen, which is a reactant. And now I've got 2 masses of reactants. So that tells me this is going to be a limiting reactant problem. So I can convert one reactant into the other to see which one will run out. This is a little different than the way Alex does it, but this might help you. Okay, so I'm just going to convert one reactant all the way over to the other and see if I have enough, okay? So I take 14 grams of methane. It doesn't matter which I start with, but I'm going to take methane and I'm going to convert it all the way over to how much oxygen I need. And then I'm going to look at the problem to see if I have enough. And I see from the balanced chemical equation that they react in a 2-to-1 ratio once I get to moles. So I got to get out of mass and into moles for methane. So getting out of lab units, I'm going to convert that to moles. That's pretty straightforward. 16 grams per mole. Now I can use the chemical equation because I've got moles. So it's a 1-to-2 ratio. So the chemical reaction, I've got 2 moles of oxygen for every 1 mole of methane. Do you see where those come from in the chemical equation? Y'all see that in the back? Okay, good. And then I get back into lab units because I need to compare grams of oxygen to what I have in the problem. So now I've got moles of oxygen, but that's not easy to use. I want to get it into a number that's easy to use. I want a number that I can compare to that 89.4. So I use the molar mass of oxygen, 32 grams per mole. And this is what I end up with. So in order to burn up all of that 14 grams of methane, I need 56 grams of oxygen. You see how now it's easy to tell which one's limiting. I can look right up there and I can say, I need 56 grams of oxygen and I've got 89. Okay. So I'm going to run out of the methane and I'm going to have a little bit of oxygen left over. Okay. So this is what I would do. Do I have it compared? Yeah. So conclusion, we only need 56 grams of oxygen, but we have 89.4 grams of oxygen. So we will run out of methane before we run out of oxygen. So methane is the limiting reactant. And just really focus on what we're saying. I mean, the limiting reactant is the one that we run out of. I've got more oxygen than I need. So this is all we've done at this point is we've determined which is the limiting reactant. We haven't finished the problem. So these problems are long in that they take 2 steps. The first step, we calculate to see which one's the limiting reactant. Then we actually answer the problem. Okay. The problem is saying how much is the maximum amount of water that can be produced by this chemical reaction. we got to know which one to start with. We start with the thing that's going to run out. So we pick the limiting reactant now, the methane, and we calculate how much water can be produced when we run out of the methane.
Where did we get the 16 grams of CH4 when we first did
the 16?
Yeah,
this one?
Yeah.
Yeah, so I had to go to the periodic table, and carbon is 12.
Okay.
And then 4 for hydrogen. So that's good. I like all these second row elements because they're so easy to add up. Like each oxygen is 16, right. And so twice that's 32. So, for things like CH4 and so on, the masses are pretty easy to calculate. But if you get up to, some of the larger molecules, you have to get out your calculator probably. I do, at least. Okay, so now let's answer the question. So, okay, well, let's take a little side trip. How would we do this if you're doing the table version? Let's go ahead and do the table version of this, deciding on which is the limiting reactant. It's longer, but I think it's illustrative. So here's our table, and we have the balanced chemical equation at the top, and then we have our change row. So methane comes down minus X, oxygen comes down with a minus 2X, water shows up at 2X rate, and then CO2 shows up with an X rate. We start out with 14 grams of methane and 89.4 grams of oxygen. 0 grams of water and 0 grams of CO2. So this is just the whole table of everything that's going on in this reaction. Okay, so then we have our molar conversion to 8.875 moles of methane. And then we can do our conversion to moles for all the oxygen. And we have 2.79 moles of oxygen. And what we want to do is we want to see what happens. Of course, we got 0 moles of those two. We want to see what happens if we run out of methane. What is X if we run out of methane? Right, it's 0.875 moles minus X equals 0 moles. So we've run out of X. So 8.75 minus something equals 0. X is going to be 0.875. What if we ran out of oxygen? It's 2.75 minus 2X equals 0. And so solving for X, it's 2.79 over 2, or 1.4. You see, this X is larger than this one. So this smallest X tells us the limiting reactant. So this is telling us that we're going to run out of methane. X, you can think of X starting at 0 and creeping up as the reaction progresses. X is a nice way to think about it. It's like the reaction coordinate. As X increases, the reaction proceeds. And when X equals 0.875, we've run out of methane and it stops. We cannot go to an X of 1.4 because we ran out of methane when X equals 0.875. And I keep showing you this not because it's the way you have to do the problem, but it's preparing you for Chem 2 when we start talking about equilibrium. So, yes.
So X, like where it says X equals 0.875, is there like an understood unit there? Or it's just...
It would be moles, but it's really, X, like in this case, it would be moles of oxygen, moles of H2O, but it's a unit of moles, if you want to think of it that way. But I like to think of it as like the coordinate of the reaction. So the methane's falling like this, and oxygen's falling at twice the rate, but I have more of it. And I run out of methane before the oxygen runs out. And so, when X is equal to 0.875, I've run out of methane. So this would be like this. Methane starts here, oxygen starts way up here. And so as X goes, methane's falling at a linear rate, oxygen's falling at twice the rate, but then methane hits 0 at 0.875, and I still have oxygen left. Yeah. That'd be a great graph for me to produce instead of doing it by my hands. Okay, so the smallest X shows that methane's the limiting reactant. And so we would use 0.875 for the whole table, and it would tell us everything. It would tell us how much oxygen's left over. It would tell us how much water's produced, which is what the question's asking. And it would tell us how much CO2 is produced, even though the question's not asking that. On the test, it might. You know what I'm saying? It could be any kind of question I could ask you would be answered by filling out this whole table. So we use that limiting reactant to calculate the theoretical yield. Now, this isn't a theoretical yield problem in name, like it doesn't say that anywhere in here, but when it says the maximum amount of water produced, you're calculating the theoretical yield for water. The theoretical yield is this phrase of, if this reaction goes to completion, what would be the yield, right? This sort of idea of, if this goes to completion, that's the theoretical part of it. Almost, I would say, very few reactions go completely to completion. And so that's why it's theoretical. If this reaction goes to completion, what would be the yield of water? That's what makes it theoretical. It's the maximum yield or the best case yield. So this is how we calculate that. We start with the limiting reactant in methane. We get out of those lab units in grams and get into moles. So we have our 16 grams per mole. It's on bottom so that the grams cancel. Then we use the chemical reaction to produce water. Last time we wanted to see how much oxygen we needed. Now we're doing the water connection. So it's 2 moles of water for every mole of methane. I'm just going slowly so you guys can keep up. Yes. Where's the sign-in sheet? It's a good question. Oh, I guess it's not. There it is. Very good. You get a sticker. Here, pick one.
Actually, okay.
Yeah, for real. If you catch a mistake, too, you get a sticker. So y'all look at my notes. All right. So then after we get to moles, then we go to water. So we want to get back into lab units to see what the maximum amount of water is. So water is 18 grams per mole. And so then we end up with 32 grams. Thanks. 32 grams of water. So that's the maximum amount of water that can be produced by the 14 grams of methane. And we have excess oxygen. It just doesn't say that in the problem. We had to figure that out. Now, if this is 32 grams of water, that's the maximum. What if we only produced 16 grams? That would be a 50% yield. So that's what we're doing with this. The theoretical yield, that's the whole. The actual yield would be the part, and then the percentage is actual over theoretical. So this is this concept of percent and actual and theoretical yields. There's 3 different types of yield. Okay. I'm going to move on. You can catch it on the video if you still. Yes.
The 56 grams from the previous be like the theoretical yield of oxygen? Or oxygen
Okay,
gas?
good question. Yeah, so the yield is restricted to the products.
Okay.
So it's what you're producing that would be your yield. I guess that would be a demand, like the amount of oxygen demanded. So you could say, we don't ask those questions at this level, but you would say, if you didn't have enough oxygen, you would say you're deficient in oxygen by a certain amount. You would calculate how much you need, and you look, it's like, well, we're deficient by half or something. You could use the same kind of concepts, but the yield is for products. Yeah. So calculating this, we took that to 0. We just did the oxygen too. So 1.04 moles of oxygen converted. Again, these are numbers you don't need in the problem, but this is everything in the table, right? If we're going to use x equals 0.875, then these are all of the numbers that you get. So here we've got 0 moles plus 2 times the 0.875 equals 1.75 moles of water. And then we multiply by the 18 grams. And this is the number that the problem was asking. We get our theoretical yield for water, 32 grams. We could do the same thing for CO2. 0 plus x equals 875. Convert to grams, 39 grams. But this green one here is the one that the problem was asking about. But you can see how in this table, this is what I was saying about being more fun than Sudoku. Once you fill all the squares, then you know everything you can know about this. And in fact, you even know how much oxygen is left over. So this is the amount of excess oxygen that you didn't use. So this is our slide sort of explaining all of the three yields. So we have the theoretical yield, the actual yield, and the percent yield. Now, I wish Alex or somebody in science would give these some standard variable names. So I just used y for yield. So that's my variable that I'm giving it. So yield is y, and I use a subscript to determine whether it's t for theoretical, a for actual, or percent for percent yield. So these are my three variables. Again, there's no standard variable like there is for energy. E is the standard variable for energy. For density, a lot of times it's rho, the Greek character rho. So there's a lot of standard variables that kind of go through science. There's really not one for yield. So I'm just for this class calling it y for yield. But pay attention to that subscript. T is for theoretical, which is the maximum. A is for actual. That's what your experiment actually produced. And the ratio of those is the percent yield. Okay. So the theoretical yield is achieved when the limiting reactant goes all the way to 0. The actual is what happens when it's not completely consumed. Now, if you think about a chemical reaction in a beaker, you got two reactants. It's going towards completion. Let's think about that methane and oxygen. It's happening, say, in a container. Once the methane starts getting chewed up, then and is producing water and CO2. Water and CO2 are clouding up the area, crowding up the dance floor, if you will, and the methane is having a hard time finding the last few oxygens, or oxygen's trying to find the last few methanes. And so that's what causes a reaction to stop before it finishes, is because the products start to interfere with the reactants finding each other. Okay, and so it just gets too crowded. And because it gets too crowded, you have an actual yield that's less than the theoretical yield. And if you take that ratio, you get the percent. So let's look at some of the Alex problems that go along with this. Well, let's see. So this is, again, completion in this table. It went all the way to 0. So all of these are theoretical yields, these two right here, the 32 and the 39. These are theoretical yields for the water and the CO2. So if only 21 grams were produced, what is the percent yield? So these are just some, if 32 is the theoretical yield and we only produced 22 or 21 grams, that 21 grams is the actual yield. That's YA. So the percent yield is YA over YT, or 21 grams over 32 grams times 100%, and we get 66% yield. And we could ask a different kind of question. What if the percent yield was 85%? That might be given in a problem. How much CO2 was produced? Okay, so we're given the percent, and we have the theoretical yield here. We need to figure out what the actual yield was. So the actual yield is the percent yield times the theoretical yield. So 85% is 0.85 times 39 grams of CO2. So we end up with 33 grams of CO2. So just working through the problems on Alex, you got to figure out what it's asking. What's this percent yield? What's the theoretical yield? What's the actual yield? And try to identify those different pieces so that you can use these equations here. Okay, how much methane remains if the percent yield is 85%? Now this one's a little tricky because 85% of it was taken away, so 15% remains. Okay, so we could do that math in our head and say, okay, 15% remains, so I'm going to take the 14 grams times 0.15 and end up with that. Or I could just do it this way, essentially the 14 grams minus the percent yield times that amount, and essentially that's what I'm taking is 1 minus the 0.85. So I'd have 2.1 grams of methane left behind. So whenever you're using a percent yield and you're taking away the reactants, that's one of the tricky ones, and Alex has a couple of those. Okay, so you got to be thinking, is this a reactant that's disappearing or a product that's being produced? So these problems do require you to engage your brain. They're not what I say, just algorithmic problems. Here's an equation, here's a variable, plug it in. Okay, those would be the like level 1 problems. Some of these percent yield problems on Alex are level 2 or level 3. You got to think through what's going on. So let's look at one. Okay, so here's the Alex problem here. The compound A reacts with compound B to form only one product, compound C. And this is interesting because we're not given any kind of moles. We can't calculate molar mass. It's uncomfortable. Even for me, I was like, man, I hate this. It's like, give me a chemical equation, right? I can't balance it. What is going on? But it says A reacts with B to perform C. And it's known the usual percent yield of C in this is 46%. So 1 gram of A is reacted with excess compound B. These are beautiful words right here. So let me just highlight that before we go any further. Whenever you see excess compound B, that means not a limiting reactant problem. And we know that because this is a percent yield problem, but still, whenever you see that in a problem, you're like, woohoo, I don't have a limiting reactant problem. So it's not a 2-part problem. It's probably just a 1-part problem. Okay, so that's always a good sign when you see that. Okay, so suppose 1 gram of A is reacted with excess B and 2.1 grams of compound C are successfully isolated. So we have 3 pieces of information that we need to discover. We need to discover what numbers in this problem, are they the theoretical yield, are they the actual yield, are they percent yield? Okay, one of them is a percent, so we know, okay, that's a percent yield. This 2.1 grams, don't know yet, but then this first problem is asking what's the theoretical yield of C. So we know that that can't be the theoretical yield, so the 2.1 has to be the actual yield. So YA is 2.1 grams and the percent yield is 46%. So how do we go about this? Well, if 2.1 grams is equal to 46% of the theoretical yield, then we can solve for that theoretical yield. So does everybody understand the logic? We're given the percent yield and we're given the actual yield. The only thing we don't know is the theoretical yield. And so we can use that equation where the actual is equal to the percent yield times the theoretical. And we know these two. So we have 2.1 grams is equal to 0.46 times YT. So we can solve for YT. So that's 2.1 over 0.46. Oh, bless you. Okay. Now this next one was tricky, and I checked my answer and got it wrong, and I disagree with Alex on this one. So I know that makes you really uncomfortable, but let's just show you how it makes me uncomfortable too. So, but there's no way Alex is right on this. Okay, so we'll go with this. So here, how much B was consumed? Okay, so this 2.1 grams of C, which was produced, consists of the amount of B plus the amount of A that reacted. Okay, conservation of mass. If I lose some A and B, it's got to show up in C. Mass is conserved. Okay, so I've got some unknown mass of B, and then this 1 gram of A was reacted, and we know that it says that the typical percent yield for this reaction is 46%. Okay, so only 46% of that A went away. So that's the mass of A that's contained in C. Okay, and I know the mass of C and I know the mass of A that went into it, and so the difference between those two would give me the mass of B. All right, so I take that 0.46 grams of A and subtract it from the 2.1 grams of C, and I get 1.6 grams of B. And so what Alex is saying is that it's 4.6 grams of C minus all of the 1 gram of A and this would be the answer that's correct, calculated correctly in Alex. But I used the 46% yield up here and got the 4.6 number. So this number is using the 46% yield. How is it using this number without the 46% yield? So this is not correct. So I don't know. It may be that I have to go in and look at the individual grades on this particular problem to see if it's caused people trouble or not. But that's the only mistake I've found in Alex so far. Okay, so let's do another one of those. In a certain compound A, or a certain reaction, compound A combines with B to produce C, no other products. And then these measurements were taken of the amounts of A and B present before and after the reaction. So here's what we started out with, and here's what we ended with. So 10 grams dropped to 0, and 5.5 grams only dropped to 2.7. Calculate the theoretical yield of C. So what are we supposed to do here? A and B combined to make C. And A went all the way to 0. So we know this is producing the maximum amount of C that's there. So how much, and the mass of C, conservation of mass, the mass of C has to be the mass of A that disappeared plus the mass of B that disappeared. So all we got to do is take the difference in A, the difference in B, and add it up, and that's the mass of C. Okay? So how much, C is just the mass of A plus mass of B. So we lost 10 grams of A, so that is now in compound C, and the difference in B is also, so 5.5 minus 2.7 is the mass of B that disappeared. It shows up in C. So 12.8 is the addition of those two. We end up with the theoretical yield for C. And that one is calculated, is correct on Alex. But does everybody understand what's going on? We don't even need to know the moles or the identity of these species. The conservation of mass is going to tell us what the final products are going to weigh. You could go back to those tables, the big table problems I have, and you could add up the masses of the methane and the oxygen and go down to the bottom row and add up those masses, and those masses would equal each other. Even after all of the chemical conversions and everything like that, conservation of mass works, even with the excess oxygen. So you'd have to add in the excess oxygen plus the CO2 plus the water, and the ending mass would equal the beginning mass. And if you find out that that's not the case, you found a mistake on my table and you get a sticker. So, okay, so let's look at this one. Suppose the percent yield in this reaction was 76%. Calculate the actual amount that was isolated at the end of the reaction. So we know that YT is 12.8 grams. And so we're going to multiply that by 0.76, and we're going to get the actual yield of 9.7 grams of C. So those of you that have tried these problems and we're having trouble, like what were you saying was confusing you about the percent yield problems? Because at the beginning of class you had some questions about it.
I think it was the first part, just the initial, like, trying to figure out what numbers do you actually need to be.
Okay. So the principle in all of these that I've noticed that Alex is really leaning into is this law of conservation of mass. So the masses of the reactants that go away, you got to figure that out, and that's going to show up in the mass of the products. So you're not going to get mass out of nowhere. If you have a mass in the product, it's got to come from the reactants. And so that's sort of an unstated law in these problems, is being able to find out, using that the product's mass equals the sum of all the reactants that went away. So that's the key principle. Okay, here's a limiting reactant in lab units with percent yield. So liquid hexane reacts with gaseous oxygen to produce carbon dioxide and water. What's the theoretical yield of carbon dioxide formed from the reaction of 67.2 grams of hexane and 166 grams of oxygen? Okay, so what do you see in this problem? I can easily identify my reactants. It says hexane reacts with oxygen. I can see my products, CO2 and water. I see a theoretical yields claimed here. Okay. And so, yeah, so theoretical yield. So we're going to calculate the maximum amount of carbon dioxide formed. And I've got two reactants listed, so it's a limiting reactant. So these are all the color codes that I have. It's a limiting reactant problem because multiple amounts are given for the reactants. Theoretical yield because it says so. Okay, and so we can jump in. All right, so balance the chemical equation. Find the limiting reactant. Use the limiting reactant to solve for the theoretical yield. So there's 3 major steps in this problem. So here's the balanced equation. So we go in. This one was pretty tricky. So let me walk you through my thinking on this one. So I start with the carbons. So I added up. There's 6 carbons here. So I put a 6 here on the CO2. And then I added up the hydrogens. So there's 4 times 2 here. So that's 8 and 6. That's 14. I think that's right. Yeah, 14. So I had a 14 here. Yeah, 8, 6. Okay, and then I add up the oxygens. So this is 2 times 6 is 12. Oxygens, 14 here. So that is 26. Is that right? Yeah, 26. Am I missing something up? Let's see. 8. 14. Oh no, this was what it was.
It was 7.
Yeah, 7. So anyway, they come in pairs, and so I had 14 hydrogens. So this was 7 water molecules. That's right. So this is how it would go along, and then I have 12 oxygens, and over here I have 7 oxygens. Okay, and so that's 19 oxygen atoms. They come in pairs, and so over here I would have 19 halves, right? So then when I get to that point in these reactions, I've got 19 halves. I don't like that 1 half, and so I multiply everything by 2. And so that's when I get the 2 here. The 19 halves becomes 19. I double the 6 and get 12. I double the 7 and get 14. Okay? Straightforward. Okay, then I find the limiting reactant. And again, one of the best ways to do that is just pick one of the reactants and convert all the way over to the other reactant to see how much I need. So let's pick the hexane since it's listed first. Get out of the lab units. So this one I had to go in and figure out 6 times 12 for the carbon plus 14. Okay, then I get to 86. All right, so then I have the chemical reaction, and I'm going from hexane to oxygen. So it's 19 oxygen moles for every 2 moles of hexane. You see why the balanced equation is necessary there, because if I don't know it's a 19-to-2 ratio, then I'm not going to be able to do this part. And then I get back into lab units out of oxygen. So I have 32 grams of oxygen per mole. And I end up with 237 grams of oxygen needed. Last time, the methane was limiting. Now the oxygen is limiting. I need 237, but look what I have. I've only got 166. So oxygen's the limiting reactant. So this is the best way. Just take one reactant, convert it all the way into the other, and then see what you've got and see if you need more or have too much. So oxygen's the limiting reactant. So that tells me now I need to start with 166 grams of oxygen to calculate the theoretical yield. So let's do that. We balance the chemical equation. We found the limiting reactant. Use the limiting reactant to solve for the theoretical yield of the product. So 166 grams of oxygen, get out of lab units and into moles. Then we use the chemical reaction. Now I'm going from oxygen to CO2. So it's 12 moles of CO2 for every 19 moles of oxygen. Let you guys catch up. And then back into lab units. It's 44 grams per mole for the CO2. It was 32 for the 2 oxygens, and then another 12 gives us 44. And so then when you multiply all of that around, we get 144 grams of CO2, and that's the theoretical yield. Notice we're calculating all of our yields in lab units, so it's grams. Okay, we're not doing our theoretical yields in moles. We're using them in mass, grams. So a limiting reactant problem is a theoretical yield problem. You calculate the maximum amount that could be produced. Okay. So what do you see in this problem? Again, we've got the gaseous, this is butane to produce carbon dioxide and water. If 0.494 grams of water is produced from the reaction of these two, calculate the percent yield. So now we got 3 numbers given in the problem, and you got to know which one's a reactant, which one's a product. So we're given 2 reactants. Okay, we got the butane here, we got oxygen here, and now we're given a mass of the product. We're like, oh man, now I got to calculate the theoretical yield and compare that to the actual yield and get the percentage. So it's a limiting reactant problem because we have multiple reactants given. An amount of product is given, which is probably going to be less than the theoretical yield. And so then we can calculate that percent. This is the hardest one we're going to do. So this is, it is what it is. So we're going to balance that reaction. Same kind of thing. These were interfering coefficients. When I get to the end, I am going to end up with 13 halves of O2, and I got to double everything. Then I pick one. I'm going to start with the butane, convert that to moles. Then I do the reaction to figure out how much oxygen I need. So it's a 13:2 ratio for this reaction. And then I'm going to get out of those moles of oxygen and into grams. So I need 2.08 grams of oxygen. And I look up there and I've got 2.9. So oxygen's the limiting reactant. I need 2.08 and I've got 2.9.
Point of butane.
Oh, wait.
Of oxygen.
Oh, yeah, that's right. I'm sorry. Yeah, I need 2.08. I've got plenty of oxygen. So the butane is the limiting reactant. Yeah. What's that? I know, he needs a sticker. There you go. That's good. Put that on your helmet. Okay, so then we use the butane. It's the limiting reactant. Get out of moles. Then do the reaction. We're looking at water. So we need to go all the way over to water, and it's a 10:2 reaction. Now you can simplify that one and divide that 10 by 2 and have a 5 on top. That's totally legal. If you're doing your calculator and everything, you can take 0.58 times 5, divide by 58, times 18, and you get your answer. Okay. So 0.9 grams of water is the maximum amount that 0.58 grams of butane can produce. And we end up with 0.494 grams actually produced. So that's the actual yield up there. And so the actual over theoretical is our percent yield. Sure looks easy when I do it up here. You're on your own, it's a lot more difficult, okay? So for 20 years, I've had students say, I wish you'd do more problems in class. So that's what I'm doing, is problems in class, okay? But don't fall into the trap. It'd be like if you're on a basketball team sitting on the bleachers watching your coach shoot free throws. Okay, it's not going to make you a better free throw shooter. I mean, you got to drill, you got to do this. So that's why that's why I'm giving substantial points for Alex, is that's when you do the problems. But I am recording these on video so that you can go back and see my logic and how I thought through the problem. Then you go back to Alex and you do your Alex work. But that takes time. So that's why I'm so stressed about people waiting until the last minute to start dialects, because you're just going to run out of time and you're going to be frustrated. You're going to like, man, I was going so well, but I ran out of time. So please just start earlier and do a little bit more every day so that it's not a big slug on the due dates. And that'll be way better. And you'll remember it better if you're, they say, how do you eat an elephant? One bite at a time. Okay. So this course is like eating an elephant. So you got to do a little bit every day, and that'll spread the work out. Okay. Any questions? We got a little bit of time left. Is there anything in there that logic-wise you guys were fuzzy on? Okay, well, I'll stay up here. You guys can go, and you can bring your questions to me. Talk to you later. Or we can go upstairs if people want to look at their exams, like if you want to go by and look those. So we can do any of those things.